Ladies and gentlemen, welcome to the second keynote session of the 2021 joint EuCNC and 6G Summit. My name is Ari Pouttu and I'm the chairperson in this session. I am a professor at the University of Oulu and I'm also the vice director of the Finnish 6G flagship started in 2018. The two keynotes that we are about to receive revolve around the recent visions and research on 6G technologies. Even though here in Oulu, in the real world, we are experiencing partial eclipse of the sun, let us give an opportunity for our keynote speakers to shed some light on 6G in virtual world. Our first speaker is Professor Roberto Verdone. He is a full professor in telecommunications at the University of Bologna, where he heads a research group performing research on radio resource management for mobile systems, medium access control, routing and topology aspects of the IoT, architectures and technologies for the IoT. And in particular, he's active in the field of intelligent IoT in 5G and 6G networks, terahertz communications and UAV-aided communications and networks. Since 2020, he's the director of the National Laboratory of Wireless Communications, WiLab, participated by about 70 researchers. He is also the co-director of the WiLab Huawei Joint Innovation Center on Intelligent IoT or 6G. It has published about 200 research papers on IEEE journals and conferences, and he has been involved and coordinated more than 10 European projects and many industrial contracts in the past 15 years. He has contributed in various roles to organizing committee of several IEEE conferences like ICC, BTC, and PIMRC. In 2014, he was the organizer and general co-chair of EuCNC, held in Bologna. He's going to talk about IoT and 6G. Professor Verdone, the virtual floor is yours.
Hello, my name is Roberto Verdone. I'm the director of WiLab, the National Laboratory of Wireless Communications of Italy. In this keynote, I will talk about the Internet of Things in the 6G era. I will try to provide my personal perspective regarding two questions. First, and this is going to be the first part of my keynote, what will be the new IoT applications of the 6G era? And second, what will be the key enabling technologies? Since we're going to talk about the Internet of Things, at first, question should be, what are the things that will be connected to the Internet in the future? There's a possible number of options, of course, because the Internet of Things is already a reality since 20 years now. So there are many different types of objects, unmanned things, which are connected to the Internet that will be connected even more in the future. But what do you think will be the new things that will be connected after 2030 to the Internet? Please take a piece of paper and write down on it with a pen your preferred answers to the first question. What are the things that will be connected to the Internet in the 6G era after 2030? And then later you will compare your own answers to my personal answer. While you take your piece of paper and the pen and you write down your ideas, let me spend 1 minute in telling you what is WiLab. As I said, it's the National Laboratory of Wireless Communications of Italy. It was founded 1 year ago in Italy, in Bologna, by the University of Bologna, the University of Ferrara, and the National Research Council, but now already gathers more than 70 researchers from different universities around Italy. We at WiLab have some partners, some industries that share our own long-term vision of wireless communications. And in particular, today I will mention Huawei. We have started with them a decennial project. It's a joint innovation center on the smart IoT for 6G, and Telecom Italia. We have several projects with them dedicated to the industrial IoT applications and to the optimization of 5G networks through self-organizing network approaches. So let's come to the first question. What will be the new IoT applications of the 6G era? Let me start by taking some figures from the white papers of the 5G ACIA. So I'm starting talking about the industrial IoT. This figure here shows 5 different applications of the industrial IoT, of the IoT applied to industrial automation. And the next figure here shows, which is taken again by the papers from 5G ACIA, shows in the columns several use cases which have been identified as the most relevant ones for the industries in the field of automation. So let me just pick a couple of them, motion control and augmented reality, to discuss their requirements. Motion control is, to me, one of the most important use cases of industrial automation. It's about connecting to the network wirelessly, moving and rotating parts of the machine in order to generate a closed loop control system, which will allow full control of all functionalities of the machine. So we have sensors which are wirelessly connected to a collector. The collector provides all information to the controller of the machine that will send commands to the actuators. The control loop can be closed on the machine or might be connected to the internet in order to get advantage of cloud services, big data services, and so on and so forth. Now, if you look at the 5G ACIA white papers and the requirements for this use case, you will see that the end-to-end latency which is required is less than half of a millisecond. And the typical reliability which is requested is in the order of 7 nines. These requirements will not be fulfilled by 5G, which, as you know, will provide a latency which will be like 1 millisecond in the RAM, and with a reliability in the order of 5 nines. So for this, we clearly need 6G. On the other hand, for another use case, like for instance augmented reality, where you have a worker commanding a robot working on a difficult or hard to reach or dangerous location, well, in this case, the requirements which have been set by the 5G ACIA are different. The end-to-end latency should be less than 10 milliseconds. The reliability should be in the order of 3 nines. These requirements are totally in line with 5G as an enabling technology. So as you can see, the industrial IoT, and in particular the control of machines in industrial IoT and industrial plants, is for sure one of the applications for which we do need to have a 6G system. On the other hand, there are other IoT applications for which we do need 6G. For instance, one of them is digital twins taken to the deep, meaning in industrial machines, again, the concept of digital twin is such that you have a model running on a computer which in real time is totally synced to the actual piece of the machine or the engine or whatever. Of course, to have this synchronism, you need to have a lot of data, so very high throughputs, from the real world to the digital world in order to have the model completely synchronized with the physical world. The concept of digital twin, of course, does not apply only to industrial machines. For instance, in the future, it will apply to cars, normal cars. And as long as all the data taken from the sensors of a car will be sent in real time to a digital twin, the digital twin will be able to predict possible maintenance events, predict possible failures. So predictive maintenance in industrial machines or in vehicular environments is actually the first answers I'm providing to the question, what will be the IoT applications for the future? But then, as long as we are talking about the vehicular context, let me mention augmented sensing, which to me is one of the most important and most challenging IoT applications of the future. With augmented sensing, the idea is that your car, having hundreds of sensors, radars, lidars, any kind of sensor, detecting the traffic in the surrounding, detecting many different physical instances, your car will share this data with all the surrounding cars. And the same will happen in the opposite direction, so that your car will take advantage of the data taken from all sensors of the cars in the vicinity. It is estimated that augmented sensing will require throughputs from each car towards the rest of the cars in the order of several hundreds of megabits per second, which means that your car will receive tens of gigabits per second of information. So clearly this requires a complexity which can be tackled by 6G networks in the future. And then finally, what about the urban sky, where many different types of drones, unmanned aerial vehicles will fly for patrolling, taxi drones and other types of drones. They will not be piloted by a human, they will be unmanned, and they will be remotely controlled by some AI. And of course this means that you have the need for very high throughput links between the drones and the network between drone and so on and so forth. So the things I'm referring to are basically industrial machines, cars, and drones. But there's still something more that I would like to mention. Cobots, collaborative robots, robots that will work in cooperation with humans. Home assistants of the next generation, humanoids in general. These are systems that will work based on some AI and will cooperate so closely with humans that will need some proper backhaul in order to provide all the data sensed by these cobots, these humanoids, to some external controller. So again, this is another type of complex thing that will require very low latency, very high throughput, high reliability requirements. And so this is another category of things that to me will be the things for IoT applications of the 6G era. So what about what you have written on your piece of paper? Is it the same? Is it better? If so, please tell me during the question and answer whether you had other ideas. Now let's go to the second part. What will be the key enabling technologies? First of all, let me start with one slide reminding you that 5G claims to be the point of convergence between the many decades of history when human-to-human communication, from the dawn of radio communications, when Marconi in Bologna made his first experiments on the radio propagation, until these days, the human-to-human communication through 1G and then 2G, 3G, 4G, and now 5G was a trend, a technological trend, which was totally independent from a totally parallel and independent trend, the technology trend, which was the one who conceived the Internet of Things. The concept of Internet of Things, though it already started many decades earlier, was somehow realized at the end of the previous century, and so it's 20 years now that we are working on the IoT. And as I said, for many decades, the human-to-human interaction systems and the systems for physical world-to-human interaction were totally parallel technology trends. Now 5G claims that will act as a point of convergence. Is it true? I must say that one of the things that those who worked on the IoT have clearly understood in the past 20 years is that one size does not fit all. There's no single technology that is good for all IoT applications because they are very, very different. They have very different requirements. So is it 5G the size that will fit all? I don't think so. Let me tell you a few words about 5G and the IoT. In the past 20 years, most enabling technologies for the IoT were first short-range technology, then low-power wide area technologies like Zigbee in the first case, LoRaWAN in the other case, or other similar technologies, which were characterized by the fact of being low power. What do I mean by low power? I mean that if you have to send, say, a payload of 10 bytes, which is the typical size of most IoT applications, with these systems, with these technologies, taking into account both the energy consumed for the transmission of one data block, one packet, and the overhead introduced by the protocols, well, they consume like 10 to the minus 3, 10 to the minus 4 joules for this packet of 10 bytes of payload. Which means that if you have a battery with a charge of, say, 10,000 joules, you can have up to 10 to the 7, 10 to the 8 samples to be transmitted. And as long as, for instance, take it as a reference for my talk, you transmit once every minute your data taken from the sensors, we're talking about a battery duration of 20 years. Now compare this to narrowband IoT. Narrowband IoT, with the same numbers, will provide a battery duration in the order of tens of days, maybe not 20, but in any case, 1 or 2 orders of magnitude worse than LoRaWAN, Zigbee. Why? Not only because platforms are necessarily more complex, but also because the protocol is more complex. With LoRaWAN, if you have to send 10 bytes of data, you switch on the transmitter, you send them. That's it. With some redundancy, of course, but there's nothing more you have to do. With narrowband IoT, if you have to send 10 bytes of data, you have to ask the scheduler at the base station, you have to handshake with the base station when to transmit. You start an handshaking which will generate a set of preambles to send, and then up to 6 messages up and down. This clearly generates a situation where the protocol complexity brings 1 order of magnitude of more energy consumed than in low power systems. And 5G is not going to be different. The first releases of boards, sensor boards based on 5G at 27 gigahertz, for instance, for millimeter wave bands, which are of interest to industrial IoT applications, they consume 1 watt of power, which is 10 times more than what you consume with LoRaWAN and Zigbee. And this is 1 order of magnitude. The other order of magnitude comes because of the protocol. So at the end, it's 2 orders of magnitude. So I don't think that 5G will be the size that will fit all. So now let's move to the actual part of the talk, where I will be talking about the 6G IoT requirements and so the enabling technologies. I will use this 5-pointed star to highlight the 5 most important requirements for the IoT in particular. First, we said it already, the battery duration, which should be large enough, and for many applications, for instance, industrial IoT, people in the industries, they don't want to change to replace the batteries every 10 days or every 20 days, should be larger than 1 year. At the opposite side of the star, throughput, very large throughput for industrial IoT, for augmented sensing. Typically, this requires a complexity which is against the need to have a large battery duration. Reliability with 7 nines. Very low latencies below 0.5 milliseconds. And then one thing more, which is somehow new with respect to 5G, and it's localization accuracy, a very precise localization accuracy. Think of the motion control application in industrial IoT cases. Think of a sensor which is located over a piston which moves very fast, and the sensor might detect that there are some bad oscillations. It might be important to know whether the bad oscillations are measured in one position or the other of the piston, which means that you need to know when the packet arrives, whether it was generated in a position or another one at a distance of few centimeters or few tens of centimeters. So again, very precise localization accuracy is one of the requirements for 6G for IoT applications. Well, LoRaWAN, for instance, from the viewpoint of this 5-pointed star, was a technology with a very good B, but very bad L, A, T, and R. 5G, on the opposite, as we pointed out already, is much better in terms of latency, even localization accuracy, throughput and reliability, but it's too bad in terms of battery duration. So here it comes 6G. 6G should be provided with a set of technologies so that for the IoT applications I mentioned, it will be better than 5G on all of them, and in particular, it will be much better in terms of battery duration. And so now it's time to discuss about which key technologies among the others might bring to these announcements. First, Terahertz communications. Terahertz communications for lower and lower latencies and higher throughputs. These curves here, which come from a paper that is currently under publication, shows the latency against the number of tags, of things, sensor-based devices, which are on an industrial IoT machine within few cubic meters from a gateway collecting the information. We compare here several protocols. With a bandwidth of 100 gigahertz, we can easily achieve a latency lower than 10 microseconds, even for a large number of tags. Of course, as you can see, depending on the protocol, the latency can be very different. But the most important fact here is, yes, indeed, we can have very low latencies at Terahertz communication, despite issues which I will mention now. This figure here shows the network throughput as a function of the number of antenna elements at the gateway. So as you can see, the network throughput, look at the set of curves which are in the upper part of the figure. Again, for different protocols, we can have a network throughput which seems to be in the order of 70, 80, or even more gigabit per second, with a bandwidth of 100 gigahertz, accounting for many impairments like phase noise, molecular noise, the typical propagation characteristics of terahertz channels. However, as the figure shows, we should never remember to put into the model the propagation delays, which is one issue for protocol designers of terahertz communications systems. Why? Because for IoT applications where you send few tens of bytes or even few hundreds of bytes each time you send a packet, the packet is so short due to the large bit rate that as a result, the propagation delay, even at distances of few meters, is much larger than the duration of the packet. And most protocols are not conceived for such a situation. And as you can see, if you forget to account for the propagation delays in the protocol, the throughput can be significantly decreased, which calls for proper protocols conceived specifically for IoT applications in 6G, accounting for the propagation delays. Now let's come back to the issue of the battery duration. We do need to introduce some random access mechanism, which is much simpler than scheduled mechanism in the access of 6G. Of course, this might generate problems in terms of reliability, which means that we have to combine to random access processes some very smart technologies at the gateway, at the collector, in order to cancel interference. So for instance, non-orthogonal multiple access with successive interference cancellation, of course, is a proper combination to achieve proper results from the viewpoint of both reliability and battery duration. This picture here shows a qualitative curves in terms of throughput as a function of the number of users which are currently managed by one 6G cell. The blue curve refers to the case without SIC. The black curve refers to the case of an ideal SIC system. Of course, as you can see, there's a very significant improvement, which brings to very high reliability. The red curve shows something in the space between the blue and the black one, and it's a system with real SIC, techniques implemented at the gateway. And of course, this is the space for the design that we are currently analyzing at YLab. Then joint communication and sensing. Joint communication and sensing is maybe one of the most important and disruptive technologies for 6G. The idea, as you know, is that the base station, not only the base station, but I'm referring here to the case of the base station, will both have communication facilities and detection abilities. 6G should be based on waveforms, for instance, chirp-based waveforms, that might at the same time allow communication with the users and allow detection with very high accuracy in order to achieve, for instance, angle of arrival estimation with a precision which is unprecedented. Range, speed estimation. So I think that joint communication and sensing will open a number of potential applications for the future in the field of IoT, and not only the IoT, which will really revolutionize the way we'll use base stations and industrial gateways for IoT applications. And then finally, I would like to mention something which again goes in the direction of emphasizing the localization concept, which should be embedded into 6G. Traffic and QoS predictions. Within 5G at YLab, together with Telecom Italia, we are currently working in the direction of using MDT data for 5G network optimization. MDT stands for minimization of drive tests. It's data which is taken from UEs, which includes the position of the UEs, taken from GPS, or in the future taken from other technologies which are embedded in your UEs, like ultra-wideband, Wi-Fi, and so on and so forth. As long as you have this data, you know exactly where the UE is, and you know what is the quality of service which is perceived at that UE. And this information is extremely relevant, because as long as it is provided every second or every few seconds to the base station, it's a huge amount of data. You can start making predictions and statistical analysis through AI of where the traffic will pop up and what is going to be the quality of service. And this means a lot of data that can be used for optimizing the network behavior in a self-organizing way, and as a result, increasing the reliability of our links. Finally, let me mention a few technologies which somehow are transversal with respect to our five-pointed star: unmanned aerial base stations. We strongly believe that in the future, in the 6G era, drones might be equipped with base stations, which might be switched on and off a la carte, depending on real needs of the traffic on the ground. For instance, drones might serve cars for augmented sensing applications. This picture here shows the results, some results we got at YLab, from real traffic measured from cars in the city of Bologna, and with 30 drones flying over the area. The picture, the diagram on the right shows the probability that a given number of base stations, on average 8, flying over drones will switch on to serve the cars better than how the terrestrial base station can do. Intelligent surfaces, of course, and AI, I'm not going to mention more regarding these technologies, will be also key enabling technologies for the IoT applications of the future. So let me move closer to the conclusion by suggesting few takeaways after my keynote. First, one size does not fit all. At least this is not going to be the case for 5G. 5G is not going to be the final solution for the IoT. What about 6G? 6G needs unscheduled MAC strategies to take advantage of simplicity with some complexity at the base station, at the gateway, in order to tackle with problems in terms of reliability. Integrated communication and sensing is an essential technology to make the network as a sensor. And finally, flying base stations. However, before I actually conclude, I would like to raise one more question. As we said, the Internet of Things is about connecting things to the Internet. But is it really needed? If you look at the applications I'm mentioning, which are different than the usual applications like smart cities, smart agriculture, very often the data you take from one thing is needed at another thing which is in the vicinity. So do we really need to be connected to the Internet? Remember that in contexts like vehicular environments, in industrial IoT applications, the risk of cybersecurity attacks from the Internet is a real problem. Of course, if you are connected to the Internet, you can connect to any user and you can take advantage of services like cloud and big data. But as long as the users are inside your network, as long as cloud and big data services will be embedded onto, why not, wireless devices connected to the 6G network locally, there's no need to be connected to the Internet. If you wish, this is a concept which is already under consideration within the 5G era, and it's the concept of non-public networks. So I believe that by making a little bit more complex the radio access network of 6G, for instance, introducing mesh architectures connecting the base stations so that they can easily exchange with very low latency information, I think that as long as the application doesn't require that, it will be possible to disconnect the IoT from the Internet. And so we shouldn't talk about the Internet of Things, but rather we should talk about something like non-public networks of things. Thank you very much.
Thank you, Professor Verdone, for a very insightful discussion on 6G and IoT. Let me check whether there are questions from the audience. None so far. But if I'll start, there are several applications that actually do not need to receive information, nor do they need to transmit information. Do you foresee that there would be a need or a solution to have in the next generation IoT, or whatever we wish to call it, a receive only or transmit only devices?
Thank you very much, Harry. Yes, it might happen that in some cases it will be possible to have things that are receive only or transmit only. The point is that the plethora of IoT application is so wide that you can imagine any different solution and many different working assumptions. And that's the basic reason why I'm used to say one size does not fit all, because you might have situations like the one you mentioned, which require specific protocol suites for managing these kinds of devices, which only are, let's say, halfway. Yes, that's true.
Yeah, okay. You discussed about this random access as a necessity for the next generation IoT solutions. Nowadays, people are looking at grant-free access. And what is, in your opinion, the difference between grant-free and this random access, or is it actually the same thing?
Yeah, it's more or less the same story. What I mean is actually something where you can transmit through a channel which is used without any need for a scheduling, performing the scheduling and then sending the grants. So it's more or less the same story. There are some interesting options which can be found in the scientific literature where, for instance, the random access channel is enriched by means of some coding mechanism which can make very easy for the receiver to detect, even in the presence of collisions, the transmissions from the IoT nodes. So there are several options under the big hat of random access or grant-free transmissions. There are several options that should be clearly analyzed. And once more, I'm not going to expect that there will be one final answer as the one that will be the optimal solution, because it will depend on the different type of application again.
Okay, thank you. One thing I noticed in your presentation, either you omit it on because you don't see it's necessary, or you just didn't have time to discuss about it. It's specifically in industrial internet applications, this time-sensitive networking and the jitter control is becoming a very, very interesting research topic and very interesting challenge to overcome in wireless channels. Now, my question is related to that. If we go towards packets that last less than 10 microseconds, does that actually make TSN obsolete, so that you can go down to so short packet lengths that you actually have the TSN capability already there?
Okay, thank you very much for the comment. Yes, you're totally right. Time-sensitive communication is a very relevant aspect for several IoT applications, in particular industrial IoT, which means that we do need to find a way to make the latency not only constrained to a maximum level, but also rather deterministic, so that we know exactly when a packet is going to be received, and we can keep under control the age of information, which is relevant for many IoT applications in the industrial environment. This is something that definitely has to be solved, but as long as the packets are very short, I don't think this will help, because then the randomness of the propagation environment will become not only something that you have to tackle on the spatial domain, on the frequency domain, but also on the time domain, meaning that if you have transmission of a super short packet along two possible paths, the difference in terms of propagation delay among the two paths will be very much relevant with respect to the size of the packet. And so this is an issue of utmost relevance, in particular for those applications where terrestrial communication will be used, like, for instance, most probably industrial IoT. I don't think terrestrial communication will be the solution, will be the frequency band for all IoT applications of 6G. 6G will move most probably to these higher frequencies, but will need also mid bands and lower bands, because there are applications where you cannot live with terrestrial communications. But for industrial IoT, I believe that above 100 gigahertz, between 100 gigahertz and 1 terahertz, this is a range of frequencies where keeping the deterministic latency will be an issue.
Great, thank you. One more quick question related to your one size does not fit all principle, which I fully agree. Let's say put standardization into a very hard place. And therefore, I was just wondering, how do you see these test environments that we have for wireless communications nowadays? Is it going to be increased in the 6G era, for instance, testing in different verticals where the requirements are immensely different from each other?
Of course, I must say I missed part of your question because there was, I guess, a network problem. But
Yes.
testing environments, yes, testing environments are extremely relevant. The more we go into the direction of having many different applications of mobile radio communications, the more we need to have very wide testing environments so that we can really see whether one enabling technology can pop up as a solution for many different applications, if not all. Indeed, this is the reason why, for instance, at YLab here in Bologna, we are building together with some stakeholders. Bologna is the second largest manufacturing area of Europe after Germany. We have lots of big industrial automation companies, and indeed we are building pilot projects with them, testing environments, because for sure, much more than in the past, we do need to make a number of tests before standardization starts. According to our plans, as everybody expect, standardization should start in, say, 4 years from now, more or less, for 6G. Well, we do need to have many large pilots before that in order to be able to really drive the standardization process.
Okay. One question from the audience is that can Professor Verdone suggest what IoT applications will still remain to be addressed in 7G? Implants, satellite, or will 6G cover them all?
7G? Come on.
A futurist question.
A very futuristic question. I think that what will remain after 6G is clearly some need in terms of proper cooperation between robots and humans, because this is something we are addressing since some time. This is something that for sure 6G will address, but this is a very long-term topic, having a very deep interaction between humans and robots, not only from the communication viewpoint, but also from the viewpoint of how to manage the proper joint behavior of the robots with respect to the humans. Because in order to properly behave with humans, you need to understand humans. You need to understand them psychologically, behaviorally. So this is for sure a very, very long-term research field.
Okay, thank you very much. I believe it's
thank you.
Can I also ask a question?
We need to go on and give Peter Vetter also a slot for presentation. And as I mentioned, our second speaker is Dr. Peter Vetter from Nokia Bell Labs. He's head of A-Lab, Access and Devices Research Lab at the Nokia Bell Labs, and he's a Bell Labs fellow. He's leading an eminent global team with the mission to invent game-changing innovations that define the future of mobile and fixed access. Under his leadership, he and his teams have realized several world-first system demonstrations in access and successfully transferred industry-leading concepts into products. After a PhD at Kent University in Belgium and postdoc at Tohoku University, Japan, he joined Alcatel, now Nokia, in Antwerp in 1993, and has been based in Murray Hill, New Jersey since 2009. Peter is going to talk about augmenting human potential in the 6G era. Dr. Vetter, the digital representation of the floor is yours.
Thanks for having me. I'm going to talk to you about how 6G will provide the essential infrastructure to augment the human capabilities. Human capabilities as in enhancing our ability to handle proximity, our ability to handle and create knowledge, and enhancing our productivity overall. So let me start with this view here. This is inspired by the book of Harari on Homo sapiens, who makes the point that our human capabilities have been shaped through human evolution, basically to become a hunter-gatherer. But over a couple of thousand of years, our human environment has changed significantly. We are now living in an urban environment, and the number of people that we deal with has enormously increased. The density has increased from 1 person per square kilometers to 100 per square kilometer, and in urban environment, even thousands of people. We were shaped as a hunter-gatherer to work and live with 150 humans. So still today, this is the amount of people that we can have resonant, effective relations with. But the number of people we interact with has diabolically increased to 100,000 of people. In a city, in a company like Nokia, where I work, 100,000 people are an email click away. But these are not the same resonant, effective relationships as the 150 immediate. Also, actually, the whole globe is within reach. You heard about the expression of 6 degrees of separation. I reckon actually in our profession, if you look on LinkedIn, we're only 2 or 3 degrees of separation away from each other. So we need help to handle and have more effective proximity with the people we interact with. Second is about knowledge. And the knowledge at the times of the hunter-gatherer pretty much stayed constant for thousands of years. There at that bay, you can go for fishing, that bear is dangerous, these berries you can eat, and pretty much that stayed constant for thousands of years. But since the Renaissance, the human knowledge has increased more than exponential. The doubling period has actually accelerated enormously. In the Industrial Revolution, it was a few decades that the human knowledge increased. A few years ago, it was within a year, and actually now it's doubling every 12 hours. And I'm really talking about knowledge, not just about collected data, but the really learned experience. So we need help to handle that. And the human brain did not evolve in the same way. Actually, what this Ebbinghaus curve says, you will have forgotten most of what I said within a month from now. So we need help. Now, the good thing about this Ebbinghaus curve is I can reuse slides, and you still hopefully find them interesting. Actually, this particular figure on productivity, I have used 2 years ago at the very first 6G summit in Levi in Finland, where I made the point that we will use ICT to enhance the productivity. Productivity as in effectiveness of manufacturing, producing goods, but pretty much everything we do as humans. So it's the goods that then are used in leisure time to play, to learn, and actually to then become more effective and more efficient in the next cycle, cycles of a week, cycles of a generation. So productivity as in outcomes per unit of input, humans, surface, raw material. And a good measure of human productivity is the GDP. And this is a graph from the book of Robert Gordon, Rise and Fall of American Growth. And it shows that in the first half of the previous century, the human productivity growth year over year has increased thanks to inventions of the second industrial revolution like transportation, car, petrochemistry, steel. So it went from 1% to more than 3%. But in the second half of the century, it declined again. The growth declined again to less than a percent. And that despite the invention of the internet, despite the emergence of mobile networks. And so what is the reason? Well, it's because the network was designed for consumers. We use the network to watch video, to do shopping, so not very productive. And so we need to change that. But since my first talk at the 6G Levy Summit, COVID happened. And during COVID, the amount of e-commerce has peaked by several tens of percent. So within 6 months, we have achieved a rise that otherwise would have taken more than 6 years. So we've seen that having an e-commerce infrastructure has been essential to keep our economy going. Now, this was only possible because the investments to roll out that infrastructure happened already more than a decade ago. And so that realization will stay, and we will see an increased and an accelerated investment in ICT. So there's basically two industries that we can distinguish. There are the physical industries, think of the retails, think of transportation, mining, and then the digital industries, think e-commerce and banking. Now, these digital industries are the ones that have the majority of the ICT investments, more than 70%, although they're only 30% of our economy. And they are at a healthy 3% growth year over year. The physical industries, they are the largest part of our economy, more than 70%, but the ICT investments are at 30%, and they are at a less than 1% productivity growth. So the whole idea of Industry 4.0 is to bring ICT technologies to enhance the productivity also in the physical industries. And so with COVID and the experience and the realization of the importance of having automation, remote access, we will see an acceleration of investment. So you see the red curve already. This is what I showed you earlier of the e-commerce infrastructure, but then also the physical industries, the lead physical industries like retail and transportation will accelerate their investment. So you see the inflection point, that purple dot, will happen 3 years earlier than initially planned. So this is based on an analysis that Bell Labs Consulting has done. And also the laggards, think agriculture, for instance. Also there, if that inflection point will happen already this decade. And so we see an inversion of ICT investment now by 2030 in the physical industries by 65% of the total ICT investment, so proportional to the size in the economy. Now, it's also important to realize that these investments will happen this decade, before 2030, before the commercial rollout of 6G. So it is very important to then think, okay, if these are 5G investments, what is the new application, the new use case that we will design 6G for? And in order to understand that better, it's good to have a look at the past and the present. And every new generation, about every decade, has optimized the use case and the application of the previous generation, enabling it to do it at better performance and at lower cost. So 3G has improved the voice services of 2G, and as a new application, provided high-speed internet access. So the new application in 4G was then enabling higher speed video, so downloading YouTube and social media, and also machine type of communication, while at the same time cost optimizing the internet access and also enabling now zero cost voice. In 5G, the new use case is industrial automation, while we improve then also on the video and allow for real-time video conferencing at scale. And now the question is, what will be the defining use case for 6G? It's important to have that new use case because that will drive the direction of the new specifications, influence how we design the future network, and also be an inspiration source for the research in that direction. So, and our thesis is that it will be a massive deployment of sensors, massive deployment of AI, and that will allow us to connect physical worlds and human biological worlds with digital twin models in the digital world. So let me explain that a bit more. But before doing that, in the theme of the proximity, productivity, and knowledge, most of these generations have addressed the augmentation of human proximity. It's actually only with 5G that we really started addressing to improve human productivity. And then with 6G, we will start improving also our capability to handle and create new knowledge. And now you may question, yeah, wasn't the high-speed access to data with 3G already improving knowledge? No, it only improved the proximity to knowledge, the access to knowledge. Whereas now in 6G with AI, ML, we will truly have augmentation of our knowledge creation. So here is another way of looking at this. So 5G has improved the connectivity between humans and machines. In 6G, thanks to the massive scale deployment of sensors, we will have a much richer connectivity of the physical world, a richer connectivity of our own biological world, and then twinning that with models in the digital world. In the digital world, where we then apply AI ML to get a better understanding in the real time of what is happening in the physical worlds. And that is important because these digital twin models, for instance, allow to transport the model. I can be transported and be with you as if I were there in a holographic experience. These digital twin models allow to understand and anticipate needs, simulate possible outcomes, and then take decisions back in the physical world for more optimal productivity. Same is true for our own biology. These sensing capabilities allow for better healthcare, but it also makes our interaction with the world more intuitive, enhancing the human-machine interface. Let me explain the importance of these digital twin models a bit more in detail. It's actually already happening in 5G. So there are already digital twin models in factories to keep the state of the machine, to anticipate the need for maintenance or repairs. And actually also in a wide area network, we see the concept emerging of digital twins of cities, and even at a precursory state, digital twins of ourselves with recording of Fitbit data and health apps. Now, it's already happening now in 5G, but in 6G it will happen at a much larger scale of sensors and AI deployment. So that will have an important impact on the architecture of the network. So you see here a simplified view of the network with the access part, the anyhole to the edge cloud, and then the IP optical transport to the centralized cloud. And now looking at the deployment of these many sensors, they will create an enormous amount of bandwidth to upload in real time data to the AI/ML digital twin models distributed over that infrastructure. And think of these digital twin models as 3D maps with layers of parametric information, but then also more abstract, self-learned models in AI/ML where we continuously update the weight factors within the AI model in one location, but also in real time across location. So this will have an enormous impact on the utilization and the bandwidth requirements of the future infrastructure. Let me now illustrate that a bit more, how we use these digital twins to optimize productivity. So first, in an example of farming. So this is an example of urban farming, vertical farms, where we reuse warehouses to install vertical farms. And so that enhances the productivity because it's close to the people that need to produce the crops So we reduce the transportation time and the need for refrigeration from 5 days to almost 0. And then you have more fresh produce delivered. We also improve the productivity, the use of water by injecting the water really at the roots of the plants. We also reduce the lifetime, the growth time from 40 days to 12 days by optimizing the light cycles. And then the overall productivity per square meter also improved by almost a factor of 400 because we are using these multiple shelves, optimize the fertilizers. And actually it's a very protected environment. We actually need 0 pesticides because there's low risk of contaminants. So in order to understand that use case better, we have built our own small vertical farm in Bell Labs in Murray Hill in New Jersey. So you see here a view of our vertical farm setup. In the upper left, the real world view. In the lower left, you see actually there's a drone flying in between those shelves. And the purpose of that drone flying between those shelves is to inspect the growth. And you see the fisheye view from the drone perspective. And then on the right-hand side, you see actually a simplified digital twin model of that setup. And you see how we remotely control autonomously from a server the flight path of the drone. You see how that the drone, thanks to localization techniques, follows a predefined path with depicted with the green lines. Now, the whole purpose of that drone flying there is really then to create a digital twin of the growth itself. And so that you see on those next view. So you see the view, the rare view or raw view of what the drone is seeing. You then see how we inspect by leaf segmentation in the lower left, how we looked at the growth quality by just looking at the colors. And then also you see how we are able by image classification to inspect the growth quality. So that is one example how we create a digital twin model of the physical world in order to optimize productivity in farming. Here is another example. So you see here the view of the conscious factory in Oulu in Finland. This is where we produce our radio systems. And here we apply these concepts of industrial automation using 5G and digital twin to keep the state of the factory. And you see humans in the factory, but they're no longer doing the production. They're no longer doing the manual tasks. That's all taken care of by the robots. The humans are there to supervise and to do the creative product improvements, the production improvements. So we do that thanks to the digital twin models. So you see here how that is our knowledge engine to keep the state of the production of the stock. And then also how we use 5G for remote control of robots, for the navigation of robots. And these automation concepts have helped to enhance the productivity. The lead time has improved by 80%. The overall productivity has improved year over year by 30%. And because we're taking out the human error and allowing for intelligent video inspection, we have reduced the number of defects by more than 50%. So overall, an enormous improvement also of the quality. So these are two examples how we use digital twins as a perfect knowledge engine to have an understanding in real time what's happening in the physical world and use that to optimize and augment our productivity. So in order to make that happen, we can already do that at some level in the 5G era, but in the 6G era, we will do that at a much larger scale. And that will allow us to augment our proximity, so sensing at a distance, sensing capabilities that human senses cannot have at very different frequency ranges, but then also augmenting our presence, our ability to represent ourselves or other things at a distance. Then our ability to augment our knowledge, to handle the knowledge. These digital twins allow us to understand what's happening in the worlds, simulate possible outcomes, anticipate needs, and then also decide on actions to take back into the worlds. Actions that allow to offload humans from the mundane tasks. Think mechanical tasks that machines are better at, but also inspection tasks like scanning thousands of images at a second and recognizing faults or doing image recognition. So offloading humans and leave machines to do what they are best at. But at the same time, also augment humans and let them do what they are best. So that means learning, solving very complex problems, being creative, and taking care of each other. And these are typically then also the things that we mostly enjoy. So to make that future happen, 6G will become the essential infrastructure. And for 6G, for that network infrastructure, we have identified 6 research vectors. So first is the AI/ML native air interface. The second is new technologies for radio, in existing spectrum and in new spectrum. Radio not only for communication, but also using the ubiquitous availability of radio as a sensor, a network as a sensor. And when we start sensing the world, we also need to trust what we communicate over that infrastructure, what we are sensing over that infrastructure. Given the different use cases, we will also have extreme connectivity in an architecture that is pretty much a network of networks, where the endpoints are again a subnetwork with very specialized requirements. And then last but not least, also an important architecture innovations, cloudifying and disaggregating, opening up an enormous set of new possibilities in architecture design. So let me go through them one by one. So here first about the native AI/ML air interface. So what is the problem that we're solving? We want to have a communication between A and B over a channel, and through decades of engineering, we came up with the well-known model of transmitter and receiver with the front end, the modulation, the coding, and then the scheduling of the MAC. And we're using AI/ML already in 5G to basically optimize these different functional blocks. Now, what we're trying to do in 6G is take a clean slate, do away with the complexity of these different functional blocks and just let the two endpoints in real time figure out how to communicate with each other. And you see how that significantly reduces the complexity of these layers, how that is also a paradigm shift on how we design radio interfaces. And we've done already first experiments in that new space with native AI/ML air interfaces in Bell Labs. You see here how how the AI/ML air interface self-learns the constellation depending on the channel conditions. Then new spectrum technologies. So first of all, new technologies in the existing bands, the low band, the mid band, and the millimeter wave that will be refurbished for 6G as we can expect. But there will also be new bands. We already talk a lot about using sub-terahertz for 6G. There's a lot of research going on, high capacity and unique sensing capabilities, and I'll get to that in a minute. But there's also a drawback. I mean, as you can see from the lower scale, the reach of those sub-terahertz wavelengths is limited to 100 meters. So it's really confined to indoor spaces. Another important use case or spectrum are the bands just above the current midband, so from 7 to 20 gigahertz, which provides us with bandwidth comparable to millimeter wave, but with a better reach. So say more than 0.5 kilometers, allowing us to do capacity enhancement from existing cell sites in urban environments. And then we can also expect that in the low band, there will be additional bands to also address the wide area coverage over multiple kilometers. So as already said, these new spectrum technologies are not only there for radio communication, but we want to look more into using the ubiquitous radio infrastructure as a sensor. Already today, we are able to do localization with wireless technologies. And you see here a proof of concept that we have built in and have tested in Arena 2036. That is an experimental factory in Stuttgart, where we use 5G for the tracking and localization in real time of a robot. And we can do that with 10 centimeter accuracy. Now, going to 6G, with the wider spectrum, with the higher frequency and the narrower beams that we can form, we will have a much higher precision. And it's not only localization, but using it as a radar, it will also give us volumetric information. And there are material-specific back reflections that we will be able to use. Is it a metal surface? Does the body contain water? Is it a mammal or a human? So combine these sensing informations with also AI/ML, and you create a radio network with a sixth sense. So staying with the industrial automation, we will also boost the requirements there, looking at the extreme networking where the end point of a network is again a network. Think machine area network, think a car area network, think a body area network. And within those area networks, you will have very extreme requirements, sometimes life-critical requirements. You don't want the brake of your car to fail, 9 reliability. And the response times need to happen also in a factory within hundreds of microseconds. And synchronicity will be even in the nanosecond range. So network of networks with very specialized requirement in specific subnetworks. And then another important architectural theme is also the disaggregation. We have already the paradigm shift to Cloud RAN that we see in 5G with O-RAN. And we have already first prototypes where we virtualize not only the core, but also the radio access network, and where we do the physical layer processing on common off-the-shelf hardware like a GPU. And we can expect new accelerators, new types of XPU processors emerge in future, and also AI/ML accelerators. And so this allows us in a flexible way, thanks to cloud-native design principles, to instantiate RAN functions like the distribution unit, the centralized unit, or the core unit on a slice-by-slice basis, scale them on a slice-by-slice basis, and optimize their location. So that's already in 5G, but the microservices approach actually allows us to do a lot more. We can now think of dissecting the RAN and the core functions and have a fresh look at the partitioning and the architecture and optimize the location and the functions themselves on a need-by-need basis. And then last but not least, the security. As the number of devices increases, as the number of networks, subnetworks increases, the fact that we have open interfaces and have components from different sources, the fact that functions run on a heterogeneous cloud, private cloud, public cloud, web-scale cloud, and that within those data centers, we have software from open source, from multi-vendors, we have different updates, patches, so an enormous surface of potential security attacks. With that goes also the use of AI/ML with its own security risks. So we need to address that in new ways, and we need to design security and trust into a zero-trust infrastructure and design these concepts from the ground up in 6G. So hereby I'm reaching the end of the talk. So it is about all about augmenting the human capabilities, for which the 6G infrastructure will be an essential network. And I talked first about the 6G era application, so connecting the worlds, the physical world and the human worlds with the digital worlds, and then also the 6G technologies, of which we have 6 research vectors. Thank you.
Thank you, Peter. Very, very interesting and insightful talk once again from you. Thank you very much. Let's see if the audience has already submitted some questions for you. Not yet, but let's ask about first about this. What kind of other effects 6G and its new properties may have? Let's think about the internet, for instance. What is your view? What about the internet protocols? Do you think that the 6G and already 5G will have some pressure for the internet protocols to change to support the whole ICT system in more profound manner?
Yeah. Ari, thanks for the question. It's a very good question, because we tend in these talks to focus a lot on the radio interface, but indeed in the 6G era, it's more than just the radio and even the architecture, it's also the network protocols. And indeed, we also need to have a fresh look at these protocols, and I want to make the link to what Roberto has presented, especially if you look at low power, and if you look at subnetworks with confined areas, you can better optimize, and there's maybe not a need for an end-to-end IP approach anymore. If the connections are terminated at a gateway, as he has shown in his, then you can have an energy optimized protocol in that segment, and then from that gateway you can have a different protocol. I think also a fresh look at designing these protocols for security. We need to look at all the aspects of the network.
Yeah. Well, now we start to receive some questions from the audience. What is the role of quantum networking and quantum cloud computing in 6G era?
So there's multiple aspects on quantum. One is quantum encryption and understanding how you can get better security. The other is the potential threat in future that quantum computers will be able to decrypt, so come up with security measures that are quantum safe, as we call them. And then third, quantum as a compute capability, the ability to do operations that even large scale, massive compute capabilities with GPU farms cannot do today. And I think we need to think of architecture as this is also a centralized compute capability in future that we will make available, similar to the way that we make GPU farms or AI/ML accelerator farms available today.
Okay. Then there's a very nice question again from audience. The question is this: can you say a few words about the cloud continuum in 6G from edge to data centers, and how far this will require interfacing / integration with the hyperscalers? Any opportunity outside of them?
Yeah, so it will be very much a heterogeneous cloud. It is an interesting question to call it a cloud continuum. There will be private clouds, there will be the edge clouds, there will be the hyperscaler clouds, and we need to be ready for different scenarios there. And that's why people talk also about the continuum of the clouds. And it remains to be seen where the applications ultimately will run, but we need to be prepared that they will run on any one of these clouds, including the radio access network. That can be on cell side cloud with compute capability on the cell side. It can be on an on-premise cloud in a private network. It can be on a service provider cloud, or it can be actually on an edge cloud and we need to be prepared with the proper abstraction layers to migrate these capabilities.
Okay. Then there is this one particularly interesting question, has also geopolitical, at least partially geopolitical, viewpoint. What do you see, your view regarding the role of non-terrestrial networks in 6G?
So it will be another way of connecting, especially the rural areas. the oceans, where it is harder to roll out terrestrial networks. So I would say, when we talk about extreme networking, as I put in my diagram, I gave the example of extreme networking to the small scale, the subnetworks, but actually equally so, the architecture need to be ready for the LEO satellite type of communications indeed.
Okay. Then there is a question about energy consumption. What would you see as the most promising technologies for drastic energy reduction as we go forward in this ICT path? And what do you see? How do you see the role of energy harvesting in 5G and 6G networks?
Yeah. So actually, since this is the last talk of this session, I would also maybe invite Roberto to chime in, because it very much goes into his area of the IoT and the low power, zero power devices that just harvest the energy from its environment. Absolutely an important area to look at for the 6G era. I would say, to enable that, we also need to look at new semiconductor material capabilities, for instance, quantum tunneling diodes as a means to have amplification at extreme low power, because you have very low reverse thresholds that you can leverage there. So absolutely important. Zero power consumption or drop and forget kind of sensors that have a lifetime of 10 years.
Roberto, any points?
Well, of course, energy harvesting is something we've been discussing for decades now. For some specific IoT applications, especially where radio distances are very short, there are promising techniques like wireless power transfer, for instance. In particular, joint communication and power transfer might be an interesting option in the future. But I know something of the technology, and so far it's still not sufficiently mature to be used, at least for 5G industrial IoT applications. Let's see in the future. For sure, this is something that has to be discussed more widely in the scientific community before it becomes mature enough.
Okay. Then there is a question, again, which probably would fit both of you gentlemen. How do you see distinguishing sensors that serve humans and those which serve machines? And what type of sensors we might see in the future?
Yeah, so the sensors for humans obviously have to go, be compatible with human bodies, and they will have to go through the FDD and government approvals, rightfully so. I would also say, since they're on body, they will have can leverage specific propagation properties that are inherent to the proximity of the human body. So not only through air, but maybe through body. So I think there's an interesting set of new research challenges that we should explore further. I also would say, so these human body sensors are very much not only for monitoring and healthcare, so our own digital twin, but also as an enhancement of the human machine interface, to make the interaction with the physical world more intuitive, and maybe even if there are the proper privacy measures in place, even have a sense of urgency. For instance, if you say, I want this, and you do a gesture, and there is an urgency that is through the AI and ML system understood there. So that's a different set from the type of sensors that you have on machines, where you have harsh environments, potentially very rapid speeds. Roberto has shown the machine area network, where on a size, so a roll-to-roll machine of say tens of meters, you have hundreds of sensors that go around untethered, because you don't want the wear and tear of brushes or so. So a different set of requirements there in terms of the mechanics also. Roberto, over to you.
Thank you. Let me leave for a while the field of the IoT. in 6G, I expect during the 6G era, so starting from 2030, I expect that new interfaces with our personal devices will be used. I mean, in 2007, somebody invented the smartphone, disruptive invention based on the screen, or the touch screen. I believe that in 10 years from now, most of our personal devices will maybe still have a touch screen, but will also use 3D holography to provide in the space in front of us the same information, much richer information than what you can have today on your smartphone. So, of course, this means that we should find a way to interact with the space in front of us with our hands. So in terms of sensors for humans, because this was the question, I think that we have to find new ways of interacting between humans and the space in our vicinity to be fully able to have some full experience using holographic, 3D holographic systems for behaving with the, connecting with the rest of the world.
Good, good. There is a more policy and let's say education-oriented question for both of you guys. Since we now see these new machine learning, deep learning, distributed learning, new ideas implemented in practice. However, most of universities are still teaching communication in a classical way. Do you see a revolution in teaching curricula in universities, or should there be a revolution of teaching curricula in universities when we talk about AI-inspired air interfaces and similar things?
No, the fundamentals and the understanding of electromagnetic propagation and the fundamentals of communication theory, please keep them on your curriculum. Let's not become lazy and think AI/ML will figure it out for you. Actually, domain expertise, for instance, in radio, can make the AI/ML methods for the radio interface more powerful. I mean, the beginning of the AI/ML research was very much an experimental research. Just let's try this algorithm, let's try this algorithm, let's see. But that's not the way forward. It's really the combination of domain expertise applied and smartly with the algorithmic understanding. So that you should add to the curriculum, the AI/ML fundamentals, and the combination of that to really get to the most optimum solution.
I'm very happy to hear such words from somebody with a wide experience from the industry viewpoint, because I must say I totally agree. The first and second level of the university degree should provide the fundamental ability to realize algorithmically how to conceive, how to design a system. And then at PhD level, students after 5 years in electronics and telecommunications should of course be exposed to the world of AI and the new trends, but the foundations for the future mobile radio networks, 5G, 6G, 7G, whatever, should lie in the technologies that we are used to talk, to discuss as we did in the past 10 years. So of course, there will be adjustments, there will be a number of improvements that we can introduce, but I don't expect that we should revolutionize the way we do teaching at universities, at least for the first two levels, as I said, bachelor and master's.
Yeah, sigh of relief on my side. Thank you very much for the comments. One more question, which is a little bit on the lighter side, and then we'll wrap up. Now, given that we start to have these sensors and network as a sensors, and then we have these powerful algorithms mining the data available everywhere, these machine learning AI algorithms. Now, the question is, how far do you believe that we can see into the future? Is it seconds, Tens of seconds.
So predicting needs and human behaviors, I think that can go fairly far. Actually, it's already happening today, for instance, in web behavior and purchasing behaviors on the web. The likes of Amazon are tracing what people are buying and what is the likelihood when you have this buying behavior, what is going to be next, and let's stock up our warehouses in the proximity of where these needs will be. So I think it is more than seconds, and we see also already precursory elements of that kind of anticipation.
Roberto, any ideas?
Let me answer with a sort of, say, non-technical answer. I mean, fortunately, the world is so complex that it is impossible to predict it. Seriously talking, in the long term. So the complexity is such that, yes, maybe you can have predictions in networks of based on statistics, based on AI, of the traffic that will come, of the QoS that the network will provide within seconds, but no more than that, as I said, fortunately.
Okay, thank you very much. And gentlemen, Professor Verdone, Dr. Vetter, I really do appreciate the discussion. And definitely, both of your presentations were really insightful and nice to hear, nice to listen presentations. Now, also, I would like to thank the audience for providing some questions. And I believe we are already 1 minute in overtime. So thank you once again, gentlemen. And I wish you a very nice afternoon. And for Peter, morning.
Thank you very much. Bye.
Bye-bye.